Welcome to the Depth Dive. Today, we're zeroing in on a real cornerstone of computational complexity.
The maximum cut problem.
Exactly. It's a challenge that, for most networks, for most graphs, finding the perfect solution is, well, it's basically out of reach.
That's right. I mean, we're talking about the algorithmic equivalent of trying to solve a puzzle where the number of possible moves is just astronomical.
So what's the actual goal here?
The goal of the max cut problem is, pretty straightforward on the surface. You're given a network any graph where the connections, the edges, have weights.
Okay.
And you need to slice it. You partition all the nodes into two sets, S and V minus S.
And the goal is to make that slice in a way that maximizes the total weight of all the edges you just cut.
Precisely. You want the cut to cross the most valuable connections.
The biggest bang for your buck, maximizing the severance. And you said this is generally out of reach? Why is that?
Well, it goes back decades. To Richard Karp, actually. Back in 1972, he published this famous list of 21 problems that really defined NP completeness.
And max cut was on that list.
For general graphs, absolutely, it's right there. Which means we have no known algorithm that can guarantee finding the optimal solution in polynomial time.
So if your network gets even a little bit bigger, the time you need to find the best answer just explodes.
It explodes exponentially.
Yeah.
You'd be waiting for the heat death of the universe to solve a really big one.
And this is exactly why the breakthrough we're talking about today is so important. Hadlock's algorithm from 1975.
It really is. Hadlock looked at a specific class of graphs, the ones with a clean geometric structure.
The planar graphs.
Planar graphs.
Yeah.
And he figured out how to transform this exponential monster into a totally manageable polynomial time problem.
It's an incredible piece of mathematical jujitsu. So the mission for this deep dive is to unpack that transformation. It all hinges on this beautiful concept of geometric duality.
It does.
How does just being able to draw your network neatly on a piece of paper completely change how hard it is to solve?
It all comes down to structure. Structure is the kryptonite for complexity. So let's start there. What is a planar graph?
It's a graph you can draw on a flat surface, like a piece of paper, without any of the edges crossing over each other.
Right. No overlaps.
Which seems like such a simple, almost trivial visual constraint. But I know it's the key to everything. Why does that give us such a huge computational advantage?
Because it lets us define something called the dual graph, which we can call d-dollars.
Okay.
Every planar graph, d-dollars, has one. And you can think of the dual graph as sort of flipping the roles. In the original graph, we care about nodes and the edges between them.
Right.
In the dual graph, we care about the faces, the enclosed regions that the drawing creates, and their connections.
So the faces of the original graph become the vertices of this new dual graph.
Exactly. And if two faces share an edge in the original, we draw a new edge connecting their corresponding vertices in the dual.
Which means every single edge in the primal graph, d-dollars, has a corresponding dual edge that literally crosses it on the drawing.
That's the crucial one-to-one mapping. Now, let's connect this back to max cut. Hadlock's approach really leveraged this property of bipartiteness.
Bipartiteness, meaning you can color the graph with just two colors.
In a sense, yeah. To get the perfect cut, we need to make sure that the edges we don't include in the cut form a bipartite graph.
And if a graph isn't bipartite, it means you can't cleanly divide the nodes into two sets, our S and VS, using those remaining edges. There's a structural flaw.
Exactly. And that flaw has a name. It's the odd cycle.
A loop in the graph with an odd number of edges, 3, 5, 7.
Right. You can't two-color a graph if it has an odd cycle. You get stuck at the end of the loop, forced to connect two nodes that should be different colors, but now they're the same.
Okay, so these odd cycles are the problem.
They're the whole problem. And here is the breakthrough. These problematic odd cycles in the primal graph, d70, they correspond directly to odd faces in the planar drawing.
Ah, so a loop of 3 edges creates a triangular face.
Exactly. And those odd faces become these really important key target vertices in our dual graph, d-dollars.
So we've mapped a combinatorial problem, finding a cycle to a geometric one, just identifying a face.
That's the leap.
That structural mapping makes sense. We know what we need to break every single odd cycle. But max cut is about maximizing the weight of the edges we keep. Here's where it gets really interesting for me. How do you turn a maximization problem into a minimization one?
This is the elegance of it. This is the complement principle, and it is the hinge of the entire algorithm. You're right. We want to maximize the weight of the edges in the cut.
Right.
But the twiddle weight of all the edges in the graph is a fixed number.
Yeah.
So maximizing what you include is mathematically identical to minimizing the weight of the edges you exclude from the cut.
Ah, okay. So we're finding the cheapest way to fix the structural flaws. We're minimizing the penalty.
That is the perfect way to put it. The penalty is the existence of those odd cycles. Hadlock's insight was if we can find the minimum weight set of edges we need to remove to break every single odd cycle,
Then the remaining structure must be bipartite.
it has to be. And the edges that are left must therefore form the maximum possible cut.
So how do we find that minimum set of cycle-breaking edges?
We use a well-known tool from computer science, the minimum weight perfect matching problem, or MWPM.
Okay.
But, and this is key, we don't solve it on the whole dual graph. We only solve it on the subgraph that's made up of those odd face vertices,
Yeah.
the ones that represent our structural flaws.
So MWPM is about finding the lowest weight set of dual edges that pairs up all of our target odd face vertices. But I'm still trying to connect the dots. Why does pairing up two odd faces with the cheapest path between them guarantee we've broken the odd cycle?
That's the core of the proof, really. Think about the dual vertices we're matching, these odd faces. The path we find between them in the dual graph corresponds, through duality, to a set of edges that form a kind of cut in the primal graph.
Okay, I think I'm following.
So when we pair up all the odd faces using this minimum weight matching, we are, in effect, finding the absolute cheapest collection of primal edges we need to cover or intersect every single odd cycle in G.
So if there's a long snaking path in my original graph that creates an odd cycle, finding the minimum weight dual path between the corresponding odd faces is like finding the cheapest, shortest line I can draw across that path to break it.
Exactly. We're finding the minimum weight fault lines needed to isolate all the structural weaknesses. By solving the MWPM problem on just that small set of odd face vertices in D dollars, Hadlock turned the intractable max cut problem on D dollars into a known solvable problem.
A problem with proven polynomial time solutions. That is such a powerful conceptual leap. And this is guaranteed to find the absolute best, the optimal cut.
It is. For planar graphs with non-negative edge weights, specifically triangulated ones, Hadlock's algorithm is proven to find the exact maximum cut. It's a guaranteed optimal solution in polynomial time. That's the win.
Okay, let's walk through this mechanically. If I'm an engineer implementing this, what are the steps?
Right, the procedure. First, you have to build the new mathematical landscape.
So step one, construct the dual graph, Dewey dollars, and you carry the weights over from the primal edges to their dual counterparts.
Correct. Step two is finding the problem spots. Identify the odd faces. These vertices in DA dollars are the only ones we care about for the main calculation. We can just ignore everything else for a moment.
Then we get to the heavy lifting. Step three.
Step three is the computational bottleneck. Compute the minimum weight perfect matching on that subgraph of odd face vertices.
Huh?
This finds the optimal pairings.
And once we have that pairing, we have to translate it back. So step four, identify the excluded edges.
Yes, those are the primal edges that correspond exactly to the matching we just found in D dollars. This is the minimum set of edges we have to sacrifice.
Which brings us to the end. Step five, form the max cut. We just take all the edges we started with in D dollars and subtract that minimum excluded set.
And what's left is your answer, the maximum possible boundary cut.
That process makes sense. But how fast are we talking? We've gone from exponential time to polynomial. What's the specific metric?
The time complexity is dominated by that MWPM step. In the worst case, it's 1n3, where n is the number of vertices.
Which is a massive, massive improvement.
It moves us from basically non-computable to solvable.
But I mean, N3Out is still pretty serious. For really enormous graphs web scale data, utility networks with millions of nodes cubing, that number is still slow.
Oh, absolutely. It would be a huge limitation if we were still just using the 1975 method. That voluntary complexity is why modern implementations don't stop there.
So what do?
They lean into the planar geometry even more. They break the problem down into smaller pieces before they even touch the MWPM solver.
So the focus now is on decomposition, making the problem smaller before you even start. What are the key techniques?
The main one is biconnected components analysis. You take the dual graph and you break it down into these subgraphs that would stay connected even if you removed any single vertex.
And why is separating the graph like that so important for speed?
Because if you can partition the graph into, say, 5 independent components, you can solve the MWPM problem on each of those smaller pieces separately.
And in parallel.
And potentially in parallel, yes. So instead of one enormous dollar problem, you're solving 5 much smaller problems. The total time drops dramatically.
And this isn't just theoretical. The empirical results show real gains. For a graph with about 150 nodes, like a small circuit board layout, the speedup is almost double.
It's about 1.85 times faster, yeah. The time drops from nearly 29 seconds to just over 15. It really shows the power of combining modern decomposition, like something called chain decomposition, with Hadlock's classic insight.
Okay, let's shift to application. The math is elegant, the implementation is fast. So what? I mean, where is this actually being used out in the world?
The most direct and critical application is in VLSI circuit design.
Very large scale integration, microchip manufacturing.
Exactly. Because chip design is inherently planar, right? You're laying out wires on a flat surface.
No crossing wires if you can help it.
You really can't. So Hadlock's algorithm is essential for two big things. Circuit partitioning, so dividing a huge circuit into manageable blocks, and even more importantly, wire routing. You use these principles to minimize crossings and maximize separation.
So every time we get a smaller, faster chip, we're sort of seeing the legacy of these algorithms.
In a very real way, yes. You're seeing the output of minimizing those crucial wire crossings.
That's a powerful connection. Where else does this pop up?
It's big in network design for load balancing in telecom systems. If a network is mostly planar, you can use Hadlock's method to find the best way to segment it for maximum data flow.
And what about in the visual world?
We see it in image processing, especially for image segmentation.
Oh, interesting.
Yeah, when you want to partition an image into regions, like separating a person from the background, you can model the image as a planar graph. The pixel boundaries are the edges. Maximizing the cut weight helps find the most natural, high contrast boundaries.
So even with this classic algorithm, what are the challenges engineers still face when they're trying to implement it today?
One that's surprisingly persistent is numerical stability. That MWPM step relies on very precise calculations with edge weights. Standard floating point math can introduce tiny rounding errors.
And they add up.
They add up, and they can lead to a solution that's just slightly suboptimal.
So how do you get around that?
Well, you can use specialized high-precision data types, like decimal types in some languages, or more simply, you just insist on using only integer weights. That gets rid of floating point errors completely.
And looking forward, how does a nearly 50-year-old algorithm play with cutting-edge tech like AI?
It acts as the ground truth. We're seeing a lot of machine learning integration. For instance, using graph neural networks, or GNNs, to sort of predict a good starting point for the cut.
So using AI to give Hadlock's algorithm a head start.
A really good head start. Exactly. It doesn't replace it, but it can guide it. And then there's the other side of it, the endless demand for speed.
Hardware acceleration.
That's it. Leveraging specialized processors, not just CPUs.
So GPUs, FPGAs.
Yes, GPUs are great for the parallel nature of the decomposition, but some companies go even further and invest in ASIC design.
Application-specific integrated circuits.
Right. Custom chips designed for one thing only, ultra-fast planar graph operations. It ensures Hadlock's elegant math isn't slowed down by inefficient hardware.
What a beautiful arc. From this fundamental, intractable problem that Richard Karp identified to Hadlock's geometric insight that lets us flip it on its head, maximizing a gain by minimizing the cost of a structural flaw.
The whole thing is really a tribute to the power of abstraction, taking a complex combinatorial goal and turning it into a clear geometric one. And this, I think, raises an important question for you, the listener, to mull over. If Hadlock could transform an NP-complete maximization problem into a solvable minimization problem, just by focusing on the cost of the structural violation, what other impossible computational problems in your world, whether it's engineering or logistics or even finance, could suddenly become tractable if you just found a way to define and minimally eliminate the core structural flaw?